Swayam Prabha. Digital India. Educated India.
Good afternoon, everybody. Today we will continue with finite volume methods. If you recall yesterday's lecture, we will start from there. The finite volume method, if you recall, we mentioned that finite volume method uses an integral form of the equation to be solved. The computational domain is divided into elementary control volumes, and the integration is performed within these elementary volumes. The method enables one to handle complex geometry without having the equations written in curvilinear coordinates. The method also preserves the conservative property. The elementary control volumes are described by the coordinates of the vertices of the quadrilaterals for 2D or hexahedrals for 3D. That means when we get complex geometry, grids are to be generated using body fitted coordinates, and then the grids are to be generated in such a way for 2D the elements or the cells are quadrilateral, and for 3D these elements are hexahedrals. Sometimes they are also called brick elements. Now, general first order equation we can write as dE dt plus dF dx plus dG dy equal to 0. For E equal to rho, F equal to rho u, and G equal to rho v, the equation will be obviously continuity equation. And if E equal to rho u, F equal to rho u square, and G equal to rho u v, then this will be inviscid momentum equation in x direction. In a similar manner, if we substitute E by rho u, F by rho u square plus P minus mu del u del x, and G by rho u v minus mu del u del y, then the equation will be, equation 12 will be then full Navier-Stokes equations, x momentum equation, x direction Navier-Stokes equations, or x direction momentum equation. And now we will try to integrate this equation del E del t plus del f del x plus del g del y over a domain. Domain may be the elementary control volume given by quadrilateral, given by ABCD, and integration will be done in this manner, equation 14. Also, we can apply Green's theorem. Green's theorem says that this domain integral of del g del x minus del f del y dx dy, these are the dependent variables, equal to f dx plus g dy. You can very easily understand that del g del x minus del f del y, in case of continuity equation, it will be substituted by del u del x plus del v del y, and accordingly we have to substitute f and g in this line integral. So if we, as I said, if we generate a body conforming grid which will be a constant eta zeta lines, or then we can identify a specific control volume, say as we have defined A, B, C, D. Now entire domain we can identify such control volumes which will have additive property, and that is how the whole domain will be covered. If we write down governing equation for one control volume that is valid for all the control volumes, and finally we will be able to get the matrix equation. So the A is the area of this quadrilateral ABCD given here, and average value of E, you recall del U del T, del E del T was the first term, and we said E is rho. So this is average value of E or rho over the entire cell ABCD. We will call, and this also we mentioned that this small control volume or the cell will be identified in such a way that its center will be the its identification, and center will be identified by ij. So if we call this cell as ij cell, then we have also written here, if E is a property over this cell, that will be written as Eij, and I and j are the identification coordinate of center of this cell. Now we mentioned it earlier, we will apply Green's theorem. Now Green's theorem means this is basically will integrate these quantities, and E is dependent on T, so del E del T, this will be separated out, and then del F del X plus del G del Y, we will apply Green's theorem on this part. So if we do that, we can write down d dt of volume integral E dv plus line integral h dot n ds, where h is the identification of the field comprising of f and g, n is a outward unit normal of segment ds. If we look at the figure, so n is the outward normal on the segment, if we call this as ds. For a segment ds equal to dxi plus dyj, on a counterclockwise contour, the outward unit normal can be calculated from this ds as dyi minus dxj divided by ds, where this is the modulus value of ds, and while the ds, this modulus value, is basically root over dx square plus dy square. Now, as we said, for continuity equation, then our f will be rho u and g will be rho v. So n dot dx will be written as f dy minus g dx. We also said earlier that continuity equation is del u del x plus del v del y. So following that, f and g will be substituted by v and u, and we can write h dot n ds equal to f dy minus g dx. So this we can write now applying Green's theorem on equation 14, where again let me repeat, E means rho, F means rho u, and G means rho v. We said that, and then we'll apply Green's theorem, and then we can write that, the time dependent part we separate out, but the volume is not, control volume is not dependent on time. So we write ddt of integral e over dv plus line integral of h dot ds, and we have h dot n ds, and we have written here that how to calculate n, which is outward unit normal vector, and how to calculate ds. From there we can write h dot n ds is f dy minus g dx, basically rho u dy minus rho v dx. So equation 16 is a statement of conservation, and for this particular choice, as I said, E equal to rho, F equal to rho u, and G equal to rho v. Then this becomes the integrated form of continuity equation, and we'll have to perform the integration now. So again, let me explain. ddt of volume integral e dv plus line integral over abcd h dot n ds equal to 0. The finite volume method is a discretization of the governing equation in integral form. In contrast to the finite difference method, which is usually applied to governing equation in differential form, here we have to perform the integration. So this we can say ddt of this integral means total area, this volume integral here per unit depth, if this volume, this is total area. So area into Eij, we mentioned it earlier that any property which is distributed over this control volume will be identified by the identification of the control volume. Identification here is Ij, so E will be Eij, and our E is rho, so basically it will substitute rho here later. Then we'll integrate over ABCD, that means over this sides of the quadrilateral, and that is what will integrate h dot n ds, that means f dy minus g dx. We got it through application of Green's theorem. So that means this h is now f dy minus g dx. So f delta y minus G delta X over AB, F delta Y minus G delta X over BC, F delta Y minus G delta X over CD, F delta Y minus G delta X over DA. That means we go along the contour, we integrate F and G over AB, BC, CD, DA. Now, basically, when you are integrating, we are integrating mass flux because F is nothing but rho into U into delta Y. That means delta Y into unit depth, that is the area through which rho into U, that that is passing through. That means U into area gives the volume and multiplied by rho gives the mass. So through the control volume we basically calculate the mass flux, total mass flux in x direction, total mass flux in y direction, and then this net mass flux will be 0. That will be the governing equation. So how to execute this? So where we have already explained it, that A is the area of this quadrilateral and A, B, C, D are the sides. Average value of E over the quadrilateral is represented by Eij, and the remaining terms are approximation for the line integral over the segments AB, BC, CD and DA. Now, when we perform the line integral on AB, the delta YAB is basically y coordinate value of B and y coordinate value of A, minus YB minus YA is the delta Y. Similarly delta XAB is x coordinate of B and x coordinate of A. So B minus XA is delta XAB. So delta YAB we have seen, delta XAB we have seen, because we'll be taking the projection of this mass in the x direction. So projection of mass which is passing through it in x direction. So and in y direction. So rho U will be multiplied through basically delta YAB into 1, and similarly rho V will be multiplied by delta XAB into 1. Now what is FAB? If we are multiplying delta YAB into FAB, FAB will be the value of F here. Now Fij is defined here, and similarly Fij minus 1 is defined here. So these are all constant I lines, these are all constant J lines. We have so J plus 1, J minus 1, J plus 1, J plus 2. This way it will be counted in J direction, and I minus 1, I plus 1, I plus 2. These are the constant lines. So which will basically be coming out of the grid that has been generated. So what will be the value of F here? That is Fij. This is, from the coordinate it is clear, I and j crossing here, Fij, and F here I j minus 1 divided by 2. So Fij minus 1 plus Fij by 2 is FAB. What will be the GAB? See, G is again Gij is here and Gij minus 1 is defined here. So average of these two is G here. G at this point, which is, we can call it GAB. So GAB is half of Gij minus 1 plus Gij, and it is 0.5 Gij minus 1 plus Gij, and then this will be multiplied by delta XAB will be the mass flux in y direction. This is G is rho V, nothing but rho V, and F is nothing but rho U. So it's interflux in X direction. U is basically X direction velocity. V is Y direction velocity. So net flux in X, mass flux in X direction, net mass flux in Y direction. That way we can calculate. Now if we go for the so the integration over basically F and G over AB we have performed. Now if we perform integration over B and C, over BC, sorry, not A and B, AB integration over BC. Now again integration over BC will be first we have to find out delta Y BC. Delta Y BC will be y coordinate of C and minus y coordinate of B, delta Y BC, and this will be multiplied with F, value of F defined here, or whatever is the representative value of F on BC. This is basically Fij plus Fi plus 1j by 2. So you can see Fij plus Fi plus 1j by 2 into the projection of y coordinate in x direction. This is delta y bc, yc minus yb. Similarly, xb minus xc will be delta xbc. Now delta xbc will be multiplied by the value of g on which is assigned on bc. Now value of g, we are going for cell-centered method. So value of g on bc is basically whatever is the value of g here, that means gij plus gi plus 1j by 2. That is the value of g here. So that value of g into delta x bc will be the flux again in x direction, and as we have mentioned that Fij plus Fi plus 1j by 2, whatever is F value here, that means rho u, multiplied by delta y bc, that is the x direction mass flux. So we have calculated these two. Then we go for integration over CD, and this integration again basically the yc minus yd will be delta ycd, and xc minus xd will be delta xcd. So that is from geometry, and then the variable, that means Fij here and Fij plus 1 is the value here. So we have to find out F value on CD, that means a value at this location, and that is half of Fij plus Fij plus 1, half of Fij plus 1 into YCD. That is again basically we are getting the projection on x plane, because this is the x direction mass flux. X plane means the plane here which is generated by YZ. Z is 1, so generated on Y. So this is again, as we are discussing, this will be YCD multiplied by F value here, and x delta x CD multiplied by the G value here. So G value will also be GI plus 1 is here, GIJ plus 1 is here. So GIJ plus GIJ plus 1 by 2. So this way we can keep calculating. We will also calculate on dA side. So similar expression for integration along dA, and then the cycle will be complete. It will be integration over ABCD. This elemental control value will be over. So we have written now all the terms, and the first term, as we said, will be the area integral, that means total area into Eij, whatever is the dependent variable, it is rho here, ddt of A into rho. So here we will write that way, and then remaining terms, time derivative is separately calculated. Special derivatives are calculated using Green's theorem. As we mentioned, that we apply Green's theorem, basically, this is the Green's theorem. However, F is rho u and G is rho v, so we get this final expression. So for the irregular grid mesh, the finite volume provides, so this is a discretized equation, a discretization using the dependent variables defined on Cartesian coordinates. So we can see all the dependent rho u, rho v, they are all dependent on, we have written the expressions on Cartesian coordinates, and so rho v, rho u, as if whatever is their value on Cartesian coordinate, we are writing that, but we are evaluating them on curvilinear coordinate by calculating net projection of mass in x direction, net projection of mass in y direction, and obviously net mass flux will be 0, and we are setting that equal to 0, plus these are all special derivatives plus the temporal derivative. So we do not transform u, v, w, etc. along the curvilinear coordinate. So we are writing it here. For the irregular grid mesh, the finite volume equation 18 provides a discretization using the dependent variables defined on Cartesian coordinates without introducing the variables on the curvilinear coordinates. Curvilinear coordinates, after coordinate transformation, the variable transformation has to be also done, and it's a quite complex process. We are not going through that route, we are going through a different route, and this is the beauty of finite volume method. So, and we have taken the first order derivatives today, and we will take second order derivative in the next lecture to understand really that it is finally, even though it is integral method, finally we are getting the equation which is equivalent to finite difference method. Now what we have done, that if this grid mesh is uniform and coincides with the lines of constant x, it is not constant eta zeta line. Instead, if it is constant x lines, that means all y's are vertical, constant y lines or x's are horizontal, and then basically Cartesian grid mesh, then this equation, which is looking so complex, if we substitute that, you will see it will become ddt of Eij plus fi plus 1j minus fi minus 1j by twice delta x plus gi j plus 1 minus gi j minus 1 by twice delta y. So this is the central difference, fi plus 1 j minus fi minus 1 j by twice delta x in x direction, and this is again central difference in y direction, gi j plus 1 minus gi j minus 1 divided by twice delta y. This is easily possible from this equation. You can try by yourself, and you can see this is plain and simple finite difference discretization. So they are equivalent. Right? This follows the integral philosophy, but final equations are equivalent, which coincides with a central difference representation for the spatial terms in equation 12. Equation 12 means this, if we say f equal to rho u, g equal to rho v equal to rho, and if we discretize it on constant x lines and constant y lines, that means on Cartesian grid, we'll get that expression del rho del t plus f I plus 1j minus fi minus 1j divided by twice delta x plus gi j plus 1 plus gi j minus 1 by twice delta y. But in the finite volume methodology, we'll get finally governing equation, which is equation 18 for the element. Now we have to vary the indices. That means I has to be varied from I equal to 1 to I max, j equal to 1 to j max, or it is usually 2 to j max minus 2 to j equal to 2 to j max minus 1, I equal to 2 to I max minus 1, because when you go to I equal to 2, already I equal to 1 point will come, and that will be the boundary point. I have similarly, when j equal to 2 will start, because j equal to 1 point will be the boundary point. When we will define equation at j equal to 2, already j equal to 1 will be included in the discretized form. So this, when we take up the practical problems, it will be even more clear how to induct the boundary condition. We mentioned it in our last lecture, how to include Neumann boundary, how to include Dirichlet boundary condition. We'll do it further, but overall philosophy, I think, is clear now. Now I will just mention one thing, that in a Cartesian coordinate, these are constant x lines are all vertical lines, or constant y lines are all horizontal lines, and we get the grid mesh. For complex geometry, we do not do that. Instead, we try to fit in body fitted coordinate, which can be called as constant zeta lines and constant eta lines. But having generated the grid, we have to analyze the properties of the grid. Now, we do not have the scope here, but if you really look at this grid, you can clearly see that although this is not, following Cartesian coordinate system, this is conforming curvilinear coordinate system, but grids have been laid in such a way that this quadrilateral is not too distorted. And if it's a rectangular or square control volume, we call it is definitely its orientation is different, but it is not too distorted. And what does it mean? That means after generating the grid, or before generating, after generating the grid, we have to test. Before generating the grid, we have to know that the curvilinear grid mesh should have these properties. One is skewness. What is called skewness? Skewness is estimate of non-orthogonality between two intersecting grid lines. Larger the skewness, larger will be truncation error. That means, as I said, instead of x equal to constant line, y equal to constant line, if we generate grid by zeta equal to constant line and eta equal to constant lines, then, depending on the location in the domain, these zeta eta lines may not be able to maintain their orthogonality, but when they deviate, this deviation will not be much. Grid generation technique has to follow that. Aspect ratio, this is maximum ratio between any two sides of a cell. So if it is quadrilateral, right, this is ratio between any two sides of a cell. So this is desirable. This stays between 6 and 20. And then adjacent cell ratio of areas of two adjacent cells. And then we have to have a check that two adjacent cells, they will keep on varying. It is never same throughout the domain, because somewhere grid density will be more, somewhere grid density will be coarser, and all such things will we have to use in order to handle a complex geometry. But as I said, the two adjacent grids, if when we focus at two adjacent quadrilateral, then their area ratio will be close to 1. It will not be 1, it will deviate, but will not deviate too much from 1. Finally, over the whole geometry, maybe if we pick up a grid at the westernmost point and another grid at the easternmost point, they may not be able to keep that ratio. But adjacent ratios of two grids will be close to unity. Now, if we follow these guidelines while generating grids, then grid properties will be such that finite volume method will be applicable with more accuracy. Inherently, accuracy will be enhanced because of these properties of the grid. So we will stop here today, and we will take up some more aspects of finite volume method in the next class. Thank you very much.